Okay, hello everyone. I'm Daniel Turull. I work in Ericsson in the Linux distribution team. And today I would like to talk a bit about the regulations that is coming, that has been already approved with the EU Cyber Resilience Act, and then talk about a bit key concepts around security and software bill of materials. And I will focus in the Yocto project on the tools that are already integrated that allows to work with security and SBOMs. And finally, some practical examples of how distributions fix security issues, and 2 short demos that are recorded, so not live. Okay, let's see. How many of you know about the EU Cyber Resilience Act? Okay, half the room. So it's a new regulation coming from the EU that the goal is to ensure that the products with digital elements placed in the EU market have fewer vulnerabilities, and then the manufacturers are responsible for the cybersecurity through the product lifetime, which means that for manufacturers, they need to have vulnerability monitoring and corrections of CVs. And then another important aspect is to improve the transparency of security on hardware and software products, which means that all products, they need to have software bill of materials if they want to be sold in Europe. There are other markets that they have similar regulations, like in the US and India, for instance. And the objective is to bring benefits for business users and consumers to have better cybersecurity. This is a EU law that was got into force in December last year, so it's already approved, and the main obligations will come in 2027. So if you have more questions, you probably should talk with your lawyers. That's not the main goal of this talk. So if we start with the different concepts that I will be talking about in this talk, we have the software bill of materials. Okay, let's do another exercise. How many people know, before reading this, what is the software bill of materials? Okay, quite good. For the rest, it's a list of components that we have in a piece of software. And basically, as all you know, the software vendors pick components from different places, open source components, proprietary software, and then they make their own product and sell it to customers. So that's basically the software bill of materials. Describe all the components that you have in your product, and that's one key component that we need to have in order to know what can be affected in the future if we have vulnerabilities. And you can compare it as a food labeling, which you have all the ingredients, and if you have any allergy, you will know, okay, I shouldn't buy this one because I have an allergy. So you could do a similar approach with software. If you take this component, let's say Log4j, then you know that you might have a problem if you use a version that had a big problem. And then I'll talk a bit about SPDX, which is an open source project hosted by the Linux Foundation. And it's basically a standard it stands for System Package Data Change. And it's a standard to communicate software bill of material in a programmatic way, and allows you to have tracking of provenance, license, security, and also other related information. I'll show an example later on. And then if we talk about security, we need to talk about the CVs. How many of you know about CVs? Okay, that's full room. So it stands for Common Vulnerability and Exposures, and it provides a system to have a uniquely identified, publicly known vulnerabilities. And then we have the identifiers that basically allows to identify the CVs. And the CV system is based on a project from MITRE, which depends on the US Department of Homeland Security, and there was some drama a few weeks ago with the founding, but kind of it was now pushed forward a year, and there are other initiatives around different parts in the world to try to solve this. And it's basically, in the CV project, we have the CNAs, the CV numbering authorities, that are responsible to generate CVs for that products. And when I checked last week, there are 457 CNAs. The kernel.org is one. We have all the distributions. most of the open source projects now are becoming also CNA because they want to control who can assign CVs to that project. Before it was some random security researcher found a bug that maybe it's not applicable, and then they were generating a CV, and it was creating load for that particular project to resolve it. So that's, and I will see that with the open source project become a CNA, it also expanded quite a lot the number of CVs that we need to process. And then here I have a map of where the locations are. And then another thing is the MVD, which is also managed by a US institution from NIST, that depends on the US Department of Commerce, that basically they have been historically improving the CV information, targeting which version of the components, the metrics of that CV, and so on. And then the last component that I want to show here, that maybe it's less known, how many people knows about BEX? Okay, not that many. So that's a new, it stands for Vulnerability Exploitable Exchange. And basically we have this BOM that it's static, that it includes all the components that we have been in our product. But then the CVs are dynamic. Well, they change every day, you get new CVs. So the vendors need to have a way to program, with a machine-readable format to be able to disclose, is this CV not affected, is it fixed, or is it under investigation? So this is becoming more common on the, around the security aspects. And then here, now I started to look at the CVs, and I'll explain a bit the data. So this, here we have the blue line, the blue box bar is the, I look at the CV project, how many, all the data is in GitHub, so you have a JSON file for each CV with the metadata, and it has around, that packages that identify around 30,000 packages, and you see that it has been growing every year for a few thousand. And then basically, then I look at the Yocto project and the Open Embedded to look at the components that we have there in the core, and then also in the in Meta Open Embedded layers for the people that know. And then also I look for the Linux kernel. And it's basically zooming out in this one that we see that also is growing year over year. And basically, this is the full set, and then we have a subset, that is the core, and then a subset of this is the Linux kernel. So you can see that the kernel, the main point here that I want to show is that the kernel is the component that has most of the vulnerabilities. No, not the most, the most CVs. And why is that? Because the kernel became a CNA last year, and then they decided to, for any potential security issue or bug fix, it will be a CV. It doesn't really matter if it's exploitable or not. They don't know how it is used, so let's be on the safe side. If it's a null reference pointer, that's a potential security issue, then let's assign it a CV. And then also they have been improving the process over the last few weeks and months. And then I look at the kernel CVs that are published by the kernel.org. And they have, and then I look at the 6 LTS versions of the kernel that we have currently supported. That was the last versions for this branch last week. And then I look at basically how many CVs are per branch and how many are fixed with a backport according to the data from the CV information, and how many are still vulnerable. And that was a bit eye-opening for some management. That even if it's a supported version, it's the latest LTS version for that particular branch, there are still quite a lot of things that are not fixed. And this is because the older that you have, well, it might be obvious for more of you, the older the release, the more things can deviate from master. So and therefore, it's more difficult to actually apply the fix. So then it remains unfixed. And then, I don't know if it's too small, but basically here I took one of the JSON files for a random CB for the kernel to show what information we have available. So we have first some description of the CB, and then we have the component that affecting. Also, another interesting thing is that now includes also the actual file that it was affected by that CB. And then we have the versions. So we have the version when the issue was created, and then when it was fixed in Git, in semantic versions. And also we have it, that's from 2 weeks ago that show up, that is still active work on that. Also with this new CP applicability that shows basically the range that it's applicable. In this one, it's just everything earlier than 6.10 or 6.11, it's affected. And then I'll go into the Yocto project. How many of you know what is the Yocto project? Okay, that's almost the whole room, so that might be quite quick. So it's basically, it's not an embedded Linux distribution, it's a tool that creates you a custom one for you. And quickly, it's a de facto standard to build embedded systems, because you can decouple the build from the target, so you can compile everything from source in your powerful servers, and then you put it in your tiny or not that tiny embedded system. And it supports a lot of different architectures, and you can customize it for performance or for security, easy to patch things, as we will see later. And then basically you have your configurations with the explanations with metadata, how to build things, and then you have your open source components, and then you have your proprietary code. You put it all in the Yocto build machinery called bitbake, and then this will generate images that you put in your devices. It can also create SDKs, application SDKs for your developers to compile applications towards your device. And here, I want to show a bit the data that you have in the recipe that is basically kind of the input how you build your stuff. So you have a summary of the metadata that you can use later. In embedded and Yocto, it's very important, the license tracking. So you have the license, so this guy is for Carl, so it has their own license. And then you have the URL, where is this package coming from. There are some special variables that can deduce from the file name which component and version it is. And then you have some additional patches that are applied on top of the original source code and everything. Well, and then the source code is also with a checksum to verify integrity when you're downloading things. And then if I go a bit into how the Yocto project has tools regarding SBOMs and security tracking. If we go to SBOM, it's already enabled by default at least in the last 2 versions of Yocto. And if not, you can enable it by inherit create SPDX. And then you will build it as usual. And since we're building everything from source, and Yocto has all the dependencies, we can create a very detailed software bill of materials with SPDX. And even you can be more detailed that include also all the sources with the checksums. So you can have an SBOM that is 3-4 times bigger than actual image that you're building. So it's a lot of information. And there is a new standard, a new SPDX version that is version 3, that is what I'm showing here. I have another example with the previous version. And it's basically the same information that we have in the metadata, for instance. We have which license it is used, then also for the CVs, for instance, we have the CP, which is the identifier that is used in the CV ID. You have also what is the software, the package version of that component, so we know how many CVs will be applicable to this one. Then also we can have So the download URL, where is this coming from? We can have patches that are applied on top of that. So in this case, you see, okay, we have applied a CV on top of this. So this all is recorded. And then if we move to the vulnerability tracking, there are two components that are already. One CV check has been there for a while, that it basically downloads the CV database from MVD, and then checks all the components that you put in your target, if they have any standing CVs. And since we know the patches that we have applied on top, then we can actually see if we have patched things or not. And then you just need to add in your local.conf, you inherit this class, and then you will run it. And then a new thing that maybe is not that known because it didn't reach an LTS yet for the Yocto project, which is Bex. That is basically a way to make this information offline, and you can then run it anytime after your build. The CV check, you need to run it during the build, but the Bex basically will extract the information. I will show a file how it looks like, and then basically you can decouple it and do post-processing later. And then basically I have a table here comparing the different status that we can get. So in both of them, you can see if the CV has been ignored or it's been patched. But of course, unpatched is only for if you are checking the CV check. And then we have a bunch of different options on details that why this is fixed or not fixed. And then some output, this output is in JSON, so then it's very easy to parse. And you can have a CV that has been ignored, and then it will tell you why you have been ignored this. Okay, this one has been ignored because this has been disabled, blah, blah, blah. Or this one has been patched. In this way, it's probably more accurate that it's not vulnerable because the version was not in range. Or we can do, okay, this has been patched, and actually it has been patched because we have put the patch to fix it. Or this is unpatched because the version is in range. So then if you generate this at build time, then you can know how many CVs are you standing, and you can basically do monitoring around. And then for Bex, it will generate a similar file. There are also tool available that is still outside the Yocto project, but with the idea to bring it in. That takes this file and then checks with the databases, and you'll get an up-to-date status of your CVs. And then here in the Yocto, in this JSON file, that it will put all the CPs for that component, and then also there's ones that has been ignored, so that's the same one as we saw before, and then the two that we saw before. And then, but this, what I was showing is kind of a Yocto-specific JSON, and then there is OpenBex, that is the standard that tries to normalize this and be able to, for any tool. And then the tool that I was showing before also can generate this kind of files, so you can then basically share this with the users of your devices. And then another thing that I wanted to talk, since I have going a bit fast, it's a new functionality that relates that I've been working on that's still not upstream, but in the process of streaming it. So I hope it will be available in the next version of Yocto. That is basically now, we saw in the kernel CB that we had the program file, so the file that is affecting that particular CB. But most of these files are not compiled. So if they're not compiled, we don't need to waste time looking and then answering that we're not affected. So basically what my patches are trying to do, they're improving the SPDX generation. Now the SPDX, when you generate the SPDX in Yocto, it will put any single file that you have in your source directory that has been used for compiling. But since we have the actual binary generated from there, we can extract the sources that has been used from it, and then basically we filter out this from the SPDX. And then if we pass this improved SPDX to a a script that basically compares the CV data with the SPDX, then we can remove a lot of CVs. And I did an experiment with all the stable versions of the kernel. And then basically I took a default kernel configuration that is in the Yocto project for QEMU x86-64. So this is also quite bloated configuration still. It's a generic configuration that is not optimized. But we can see a drop in CVs like 60-70% just, so you're cleaning a lot of noise just by running this. And then you see the older the kernel, the more you still have pending, but yeah. Then your teams don't need to spend that much time answering things that are not applicable and focus on things that are. And then basically, the script basically adds a new entry in the CV report saying, okay, we have ignored this because it's not applicable config. And then we put the source description, source code not compiled by config, and basically this one was affecting some video driver that QEMU is not using. And then if we go to the user space, how the distributions are usually fixing the CVs. So there is the normal flow, you have the vulnerability has been found, and then it's notified to the vendor and the project. And then a new CV is created, and then usually there is an embargo period, and then the CV is released. And then the distributions, the main goal of the distribution, this version of the distribution, that this needs to be backward compatible within that major distribution. So most of the time, the newer version might be not compatible or add new features, or it might increase size. So what a lot of distributions are doing, they're backporting the fix to the version that they actually use. Or then also they can upgrade to a newer minor version. If it's too complex, it might be that it's not even fixed. And then basically how Yocto, well, in Yocto is basically done, and then anyone can contribute in the mailing list to get them fixed. So you have the original fix that has been done upstream. And then basically, that might be a bit small, but basically we have, that's the same recipe that I was showing before, and then we have the patch pointing to the fix. And then for the Yocto to know that it's actually a fix, we have some extra metadata in the patch. You see you have the original patch that's from the upstream project. And then, okay, this is a CV, that's CV, and then also all the patches in Yocto also they keep the upstream status. So in this case, it has been a backport from this commit, so we can track back actually when this was fixed. And it might be also the upstream status that is pending, which means it has been submitted upstream, or it can be inappropriate because it's Yocto specific. But most of the CVs are backports. And then I have demo time. Let's see if I can start playing this. Here. So that's maybe it's a bit small. That's the feature that I'm trying to upstream. So basically, we'll look at the configuration. Now we have Bex, and we also include the sources. So that's basically still without any improvements, and then we'll build the kernel. It will go quite fast because actually I did it just before the demo, so it doesn't need to build everything. It's just taking everything from cache. And then let me put it like this. So now it built, and then I look at the size of the SPDX. So it's 156 megabytes just for the kernel and all the files, so it's quite big. Also, one of the things that my patch is doing is reducing the SPDX size when you're adding all the files. And then also we'll look now at the report. And basically, since we generated Bex, there are no unpatched because we don't know the information. But then it will run, I think what I was doing now. Now we'll run the script that is submitted, looking at the database that we have from the kernel.org. I have the link later. So we have 86,000 files, source code. And then basically we had 132 vulnerable CVs. And then it created a new file with the summary. And then it will show the unpatched ones and why it's unpatched and where the fix is, so you can actually backport it if you are actually wanted to do it. And then for things that are, that was one example, that file was not even in the SPDX. And then we'll run the same thing with this new option that I add with the include compile sources. That will only include the compile sources. We'll rebuild the kernel to generate the SPDX. It's taking everything from cache, so you can see that it's extremely fast to build the kernel because it's not building anything. And then if we look at the size of the SPDX, now it's 61 megabytes. So we have much less files that are actually compiled in this kernel. And if I run the same script, then we get around 33,000 files instead of the 86,000 files. And we only have 45 standing CVs. And 88 has been even not applicable. And then if we look at a lot of the CVs that are not applicable, it has the source code that was not applicable. So that's demo number 1. And then I have another one with the CV check and Bex, that basically it's kind of running. If you want to have it in build time, then now we'll add we have the CV check. And then we need to run bitbake and then core image. In this case, we'll run it for the whole a minimal image that Yocto provides. And then we run all CV check. This doesn't build the image itself, but it just will look at, for all the components included, how many are in the affected. And if you see, there are some warnings showing up that are the different components that are affected. This last one is the kernel. And then you can also, if we look at and then it generates the summary file with I was showing in the slides with all the, yeah, actually, I don't remember. So that, I'm looking at this one that has been fixed. So now what we'll do, we'll actually remove this patch. And then we'll run the CV check again, and we'll see that it's actually not fixed. So that's in a way to show how adding the patches, then you can have the metadata that you need for then you need to trust that the metadata that you have in your patch is actually correct. But you need to put the trust somewhere. So now it's running the CV check again. And then if we look at the components, and I think we'll have the one that was patched before, now it's unpatched. And then, I think probably can stop here. Then we have also the Bex, but it's basically showing similar information. So to wrap up, the software bill of materials and vulnerability handling are here to stay. And I believe automation is key to survive the overflow of CVs, especially for the things that you can do it but are repetitive and you have the metadata, so we need good metadata. And also an important thing is to keep updating your components. Even if it's an LTS version of the kernel, it doesn't mean that you have all the CVEs fixed. And basically, for the distributions, most of the CVEs are fixed upstream first, and then are backported for the Linux distribution. So if there is no fix available, it's hard for the distributions to take it. So thanks for your attention. If you have any questions.
So I assume the planning for Vex is to be able to have a built baseline that you've shipped out and then be able to test and test again to find out when there's actually an exploit arriving in.
Yeah, exactly. So the Vex is static.
Yeah.
Well, for the ones that are patched, and then you run it with the scanner, and then the all unpatched ones will show up later in the future.
Yeah, so good. Anybody? All the way over there.
All the way up.
Fuck's sake. Someone.
Yeah, up there.
So I think many people are here. I'm glad Christoph is in the room because he'd give me a bad look for even asking this question. Out of tree kernels, they're a problem.
Yes.
But BSPs quite often use out of tree kernels.
Yes.
So what sort of visibility do all of these systems have for that? Like, are there CVEs for out of tree kernels? Are they just a wormhole you want to avoid? What's your position on that?
Well, my position, with these tools, you don't see the CVs in that out of tree kernels because mostly they are not publicly available, so there is not.
Well, there are some.
Well, there can be some, but the information that this tool is using is the one provided by the kernel CNA. And the kernel.org, they don't have access to all this out of tree kernels, so then the information is not available. So there is a kind of a gap there to fill.
But if there's like, someone who provides, a company provides an open source, a second tree.
Yes.
Are those monitored by Meter, by other companies, or?
Well, then in this case, the company providing this second tree, they should, if there is a CVE in their code, they should make it up. The vendor, if we look back in the CVE, I don't know if it will be. Here. So we have product Linux, vendor Linux. If the vendor is not the Linux kernel, so kernel.org, then a vendor will be different than Linux.
I see.
It'd be the one providing the out of tree.
Okay. And then if they have any additional patches for that, it's their responsibility for it.
Yes.
Okay.
I think this functionality with checking the kernel configuration with the compiled files, this is really cool. I'm just wondering how well can it work? Where does the data come from? Like, I mean, I guess it's only valid for the current kernel where it was fixed, like for master. But the file names, they might be different in the downstream or, well, in the stable kernel that you might be using, right? And do you just assume that files are never renamed, or is there some magic happening? Or is even in the kernel CNA providing some information about this?
Yeah, you see this is the kernels.org, then there is a repository called Linux security bones.git, and then here you have a CV folder with the published ones, and then you have them per year. So this is the information that we use. And then if we take one random, and then I take a JSON file, so we have the Linux, and then it's affecting this net filter. These are the affected versions in Git, and then we have the same thing with numeric versions. So you have the 5.4, 5.10, 5.15, and then also when the original fix was done, and then you have also similar information with the ranges. That's quite new. That's like 2 weeks old. this new extra field with the version starting and the version fixing it. And you have it for all the LTS, all the supported branches from the kernel. Of course, if you go out of trees, then that information is not longer valid if you are modifying things. But
yeah, so yeah, so I can speak from experience because I've been looking at this. And for the later kernels, the data is very good. For earlier kernels, the data is pretty okay, but sometimes it's not there. So it's the wrong file. It says it's vulnerable, but it doesn't because the code was never merged that it's based on. So the older kernel you get, the worse it gets.
Yeah, and what I have been seeing in the last few weeks that the kernel is taking ownership of the old CVs, and then they're running the scripts to generate this, and a lot of the old CVs, they became rejected. So there is active work fixing that.
So, yeah, the kernel is taking responsibility over this stuff. It has become a CNA. But in the end, it is not liable, right? You can't sue kernel.org.
No.
No. So, I mean, how can you trust this piece of information to the final bit of?
That's one source of information. Then you have to combine it. If you are really dependent on that, you might need other sources of information. But that's information from the open source community. Yeah. And also I might say the comment from Andreas that since the kernel became a CNA, they don't release a CVE until it's fixed. Only when it's fixed in master, then it became a CVE. So there is no. For the older ones, might be still possible, but for the new ones, now it's only, if there is a fix available, there will be a CVE. Otherwise, first there is a fix, and then it becomes a CVE.
Yeah, so, speaking to Bogdan's observation, yes, there might be misdirection in the newer, but the older way where the kernel.org was not involved was even worse and very much a sad state. So this is much better.
Is your newfound awareness about ACVs the reason you run Windows?
That's a company laptop. It's good to make present. I know that this comment will come.
More questions?
It's seen expensive terminal server.
All right. Yeah. Okay. Thank you very much.
Thank you.
So now.